Hello, welcome to the functional programming course, and this time we will talk about really important concept called closure. Let's start with an example. Suppose I want to define the function which computes the derivative, numerical derivative of any other function. So I would call this function deriv, and it would take the function f, and it would also take some small variable dx, which will define like how big I want this interval for computing derivative to be. So what I would do, I would then return a function of x, which computes f of x plus dx minus f of x divided by dx. This is pretty obvious definition, but in real life, I would probably want to fix some value of dx and use it throughout my program. And as we know in the functional programming, we can use partial application. So we can call this function deriv with, for example, 0.01. And we will define this operator d, which will then be able to apply to any other function to compute the derivative. This is all you know, but let's think about how this is implemented inside the compiler. Because when I do the partial application, the original function is still defined here. And if I take this 0.01, during partial application, in fact, I need to substitute this dx for this value and compute this expression. So in real life, what happens is that, of course, no actual substitution takes place, but we store this value of 0.01 and we associate it with the parameter dx. And then we know that we need to call this function deriv with dx equals 0.01. So in fact, we need to define this function d. We need to store the value of dx equals 0.01 and the function deriv, which we need to call. So this pair of the function and so-called context is called the closure. And we can think of some other examples. For example, if you want to define the function divisible by n, which will filter the list of values and leave only those values which are divisible by n. And then, for example, we define function filled, which is divisible by 3. This 3, again, needs to be captured and stored in the context when calling the function filled. So let's talk about that in a little bit more detail. So suppose I have some kind of variable definitions here. I say let x equals 1. And then I define the function let adder y equals x plus y. So what happens here if I do that? This function adder uses the variable x, which is external to it, which is a free non-bound variable. So now, of course, if I say adder 1, it will give me, so let me say adder 2, it will give me the value of 3. But when I define this function, what happened? I needed to capture the value of x. So all variables which were defined externally, which are used inside the function, they need to be captured inside the closure. And this adder becomes a closure, which we then able to use. Because in functional programming we don't have variables, we do not need to decide like what happens if I change the value of x. Of course, I can write here let x equals 2. And this will not change anything because this x would be a completely different x, right? If I write the let expressions, I just define additional name which masks the original name in the scope, in the lexical scope. But nothing else will happen. In traditional programming language, the question is much more fundamental because in traditional programming language, I can change the value of the variable. So let's summarize. The closure is the pair of function plus all external variables which are used inside this function, which is called a context. Sometimes it's called lexical closure because I need to include all variables which were defined lexically before this function. So partial application also creates a closure, even though I might not have explicitly defined variables, but I need to store something to associate it with the function. And I also this is also called static binding because we capture the value of all external variables at the moment of function definition, right? So how this looks in traditional programming language? Let me change this a little bit. In F#, there is something called mutable variables. That is definitely something non-functional which should not be used, preferably. But to imitate the normal programming language, I would define x as a mutable variable. So if I run this code, it would still work in the same way. But now suppose I assign to x another value. I assigned value 2 to x. So now if I run adder2, it would give me 4. You see, what happened here is that x is the mutable variable. And when I defined this function, in fact, it is not value which is stored here, but the reference to the original variable. So you can consider a mutable variable as the pointer to the place in memory. And whenever I use it, I need to take the value from that place in memory. And that is what happens in many traditional programming languages. When I change some kind of external variable, the behavior of the function changes as well. If I want to talk about closures in traditional programming languages, it also means that I want to be able to capture the current value of variables which are there during function definitions. And sometimes in some programming languages you need and you are able to do that using some specific programming language concepts. So, for example, to implement this dynamic binding, this using the current values of variables, it is much easier than constructing a closure, because in closure you need to explicitly construct this pair of a function and the context. And in some early programming languages like Lisp, in Lisp there were variables which changed their values. So to construct closures, you needed to use special keyword which explicitly constructed closures from the function. So it essentially took all the internal variables, stored the values, and constructed this structure called closure. In F#, it happens automatically behind the scenes, so you don't need to worry about that. And actually, the whole difference between closure and just function definition becomes a little bit blurred, because when you cannot change the variables of a function, you can expect them to always be like equal to the original value, and you can think of that as of something which always returns back to the original values of variables. But still, it is quite important to keep in mind that closures, especially during partial applications, allow you to store some values associated with this object, with the closure. An interesting idea related to partial applications and closures is called program specialization. The idea is that sometimes when we have a function, calling it with certain specific parameters can be defined more efficiently than the original more generic function. For example, suppose we have the function of x to the power of n. If we call it with n equals 0, the function becomes really easy. We need to return 1. If we call it with n equals 1, we just need to return x. If we call it with n equals 2, we just need to return x times x. And those implementations are more efficient than having a loop, a generic loop. So this idea of program specialization is that sometimes it makes sense to consider those specific values, and that would allow us to optimize the program. That is the idea of supercompilation, which was proposed by Russian scientist Valentin Turchin, the inventor of Refal programming language. So the idea of supercompilation is that we can take the program and then we can execute it on some kind of virtual machine and trace all the execution paths and see which values are used and passed to the functions. And we can replace then the calls with some specific values by their optimized versions and create more efficient program. That technique was first applied in the language Refal, which is kind of similar in a sense to functional programming languages, and then lately also applied to Java and some more industrial languages. So another interesting idea is called specialized program. So suppose I have the program P. The program P can be considered as a mapping from some set of inputs to some set of outputs. Now suppose some inputs are kind of static, they don't change often, and some inputs are dynamic. And the great idea is so-called Futamura projection. For example, when we have the interpreter for a programming language, suppose we have like basic interpreter or interpreter for Python, and this interpreter takes the source code of the original program in that language, and then the input values which are required by the program, and produces the output. And normally, when I write a program, the source code does not change very often, but we run the program several times and we change the input data to the program. So we can consider the source to be kind of static input to the program, and this input to be dynamic input to the program. And if we think about partial application, we can partially apply our program P to this static values. And this partial application of our interpreters to the source code of the program would correspond to the compiled program, right? So if we have, for example, super compiler, we are able to pass this specific source program, this specific source of the program to our interpreter, and then optimize that code altogether to produce more efficient compiled version of the program. And this compiled version of the program would take the input and produce the output. This technique right now doesn't really work completely in practice, but some ideas from that are used in JIT compilation in producing more efficient versions of the program and in program optimization. The reason we talked about that is that you can think about functional programming concepts like partial application in the sense of more higher order concepts. Like we used to see partial applications in simple examples like derivatives or list operations, but functions can be thought of, they can be more complex. They can accept source codes of the programs, and then we can think about some more higher level concepts like interpreters, compilers using the same kind of language and the same kind of thought process. So that is why functional programming is useful to keep in mind, even though you might not be programming the real functional programming language.